Hi class, and here is a video tutorial for assignment 9 hints for APSC248, and let's start with problem number 1. Okay, so problem 1 is find the work done by the vector force, the vector fields over the curve in the direction of increasing t. So the vector field here we consider that as a force field. Okay, and part A is fairly straightforward, and it's basically an application of vector line integral, the formula. Okay, so there are different kind of formula, and you just have to pick up one that you think it works best for you. Okay, so this is essentially all the writing here is their equivalent. Okay, now you do have RT, which is the parametric equation for the curve provided over here, so you can definitely compute the R prime here. Okay, so how about this F here? So the F here, you need to replace the XY, the Y, the YZ, the component of vector fields with your X of t, Y of t, and Z of t. So here's XY here. So XY, so basically X of t is t, and Y of t is t squared, and Z of t is t. So F vector field is t squared plus t squared minus yz t squared t, like that. Okay, so t cubed t squared minus t squared, and this is your F vector. Sorry, this is t cubed. Okay, so now do the dot product with your r prime t and do the integral, and the change of t is from 0 to 1, and you'll be able to do the vector line integral. For part B, it's a similar procedure. Okay, the only thing I can see you might experience a little difficulty is when you do the same thing, and you will have your line integral end up with something like this. Okay, so you have your line integral end up with t cosine t and sine t cosine square t plus 2 sine t dt. Okay, so how do I integrate this one here? Well, I guess you shouldn't have any problem integrating this function. And for this portion here, t cosine t, you need to use the integral by parts to do the integral. Okay, integrate by parts. And for integral of this one here, then you need to use substitution rule. Okay, so basically let u equal to cosine t, and you should be able to do that. Okay, let u equal to cosine t. Yep, that's right. Okay, so that's problem number 1. Okay, then you should be able to do the integral. Let's take a look at problem number 2. This one here is line equal, still line equal, and the work. Okay, the only problem thing is the curve C. Okay. The curve C is giving us a parabola at y equal to 5x squared, so I didn't give you the parametric equation for the curve C. You need to parameterize the curve C, and it's fairly simple. So for part A, what's the parametric equation for curve C? Okay. Parametric equation, this is a plane case, so apparently it's going to be just x over t, y over t, like that. Okay, now because y equal to 5x squared, so there are actually infinite number of ways to parameterize this guy here, but one way of doing parameterize is basically you let x over t equal to t. Okay, then y over t is just 5t squared, right? Okay, and the point changes from a to b, and x changes from 0 to 2, so which means your t value will vary from 0 to 2. Okay, so now you have your r of t, then you can calculate the r prime of t, and you can substitute into f vector fields and do the line integral calculation. Okay, and for part B, okay, we said the curve C is a shortest path from A to B. So in other words, A is the origin basically. Okay, B is here, which is 220. Okay, so shortest path means it's just the distance, right, from A to B. And your part in part A, the curve is this, right? That's the part A curve. Okay. So now you have this curve here in part B from A to B. So it's a straight line. Okay. So the straight line equation is y equal to 10x apparently. Okay. And if you want to parameterize that, then there are different ways of doing parameterizing it. And one way is, of course, you let x equal to t, and y will be 10t. Or if you let x equal to 2t, and y is 20t, right? And of course, for this guy here, and the t is between 0 and 2. For this guy here, t is between 0 and 1. Okay, yeah. Depends on your parametric equation. Okay, so basically this is going to be your r of t. Okay, for this curve. So this one here. The rest of things is procedural. You just have to substitute into your line integral formula and calculate this line integral. Okay. And part C. Okay, for part C is what I want you to provide you some hints here. Okay. So part C, let's give it a little more room. Okay. So part C has three curves. Okay, so three curves. So the first part of one curve C is from 0, 0, 0 to 1, 1, 0. Okay, and C2 is 1, 1, 0 to 1, 1, 1. And C3 is from 1, 1, 1 to 0, 0, 0. Okay. I guess if I draw it out, so here's your origin here, and it goes to 1, 1, 0. Okay, and from 1, 1, 0 it goes up to 1, 1, 1. Okay, and from 1, 1, 1 you go back to here. Okay, so the so the C1, C2, and C3. Okay, so now in this question again, I guess, yeah, this question did give you the parametric equation, okay, for any one of them, and you need to obtain the parametric equation for curve C1, C2, C3. Okay. There are different kind of solutions for parametric equation. Okay, this is a kind of exercise you have went through when we were doing scalar line integral. Okay, so let's see for C1, what will be the line integral? What will be the parametric equation for C1? Okay, C1, so z value is not changing, always 0, and xy is changing from 0 to 1. So you can just see r1 of t equals to, okay, equals to ti plus tj, right? And t is changing from 0 to 1. Okay. For C2, okay, is from here to here. So xy value kept at 1, 1, but the z value changed from 0 to 1. So r of 2t is going to be 1, or I hat plus g hat plus t k hat. Okay, so t changed from 0 to 1. Okay, now C3, now this is a part you need to be careful here. Okay, C3 is from this point to this point instead of from their origin to this point. So let's see if I call this point, let me see if A, this is B, okay, that's O point. Okay, so from B point to O point. Okay. Okay, yeah. So the the R3 parametric equation, okay, from here to here, okay, one option you can do is just 1 minus t I hat 1 minus t j hat plus 1 minus t and key hat. Okay, t value change from 0 to 1. Yeah, it's fairly simple because when t is 0, right, all you have here is 1, 1, 1. When t is 1, you have 0, 0, 0. Basically, that indicates you're going from point B to point O. Okay, so this is one way of doing this. Okay, the other way is the other parametric equation you could also have here. You see, if I go from the other direction from point O to B, okay, so basically from 0, 0, 0 to 1, 1, 1, then I could have, let's see, R3 of t, which is going to be t I hat plus t g hat plus t key hat. Okay, well, you see, well, this is not C3. This is not C3, right? This is the inverse of C3, so that's why I put a negative C3 here. Okay, so that could be another option here, but in this case, of course, that's negative C3. T is changed from 0 to 1. Okay, so, but we're gonna stick to these three here in solving this line integral. Okay, so you can make use of any one of them to solve line integral here. Okay, but if you use this guy here, then be careful of the negative sign there. Okay, the negative sign. So you're integrating not with respect, you're integrating with respect to negative C3 there. Okay, so the idea is basically parametric equation is not unique. Okay, you could have multiple choices. Okay. The vector field is not conservative, so the addition of the line integral along the three curves won't be 0. Okay, so the line integral for C1 is going to be 1 over 2, and for C2 is going to be 2, and for C3 is going to be negative 1. Okay, so check your answer, see if you have the right ones there. Okay. So let's take a look at problem number 3. Okay, this is an exercise of verifying whether a vector field is conservative or not. To verify this is all of them 3D case here, and essentially I want you to make use of the theorem. So if this guy is 0, okay, then we said the vector field is conservative, and the cross product is 0. We end up with 3 equality here. So dp over dy equal to dn over dz, and the other one is dm over dz equal to dp over dx, and the last one is dn over dx equal to dm over dy. So you need to verify the 3 equalities. So what are the m and p? M and p is, this is m, this is n, and this is p. That's what our notation is defined. Okay, so the x component is m, y component is n, and this component is p. Okay, it's really not much tricky, and it just had to calculate all the partial derivatives. Okay, but I think as I pointed out, when you do, let's for example number 2, right? When you calculate the partial derivative, this is m, this is n, this is p. So let's see here, dp over dy, this is p. So let's say for part 2, p is x sine z, okay, and n is, I'm sorry, p is, so m is y sine z, okay, n is x sine z, and p is xy cosine z. Okay, so dp over dy, what do? You consider x and z as x. So dp over dy, so you consider basically x and z as constants, right? So if x, z are constant and sine z are constant, so these two are constants, so what you're going to get is just x sine z. Okay? And dn over dz, you consider x as constants, so apparently you're going to get hang on a sec. Oh, this is cosine z. Sorry, what's going on here? This is cosine z. Okay. Right. dn over dz here, and this is a cosine z, sorry. So x sine z, right? So you consider x as constant, right? So the cosine z. Okay. So they're the same. Okay. So you can keep going, and you'll see for part 2 it's a conservative field. Okay. And same thing for part 4. You know, when you do partial derivative, you need to consider the other variables as constants. Okay. So that's problem number 3. Now let's take a look at problem number 4. Problem 4 is for what value of b and c will this field be conservative, or just we can also call that grading field. And also for trying to find the potential function for that vector fields. Calculate line integral when we're trying to go over a smooth curve joining 2 points. Okay. For the part A is again an exercise of the equalities over here. Use the equalities. Okay. Then solve for values b and c. Okay. This is fairly straightforward. I don't think you should have any difficulty there. You'll be able to get b and c as 2 and 4. B is 2, c is 2. Okay, so the focus is actually on obtaining the potential function for the vector field. In other words, the vector field f comes from the grading operation of the scalar function f. Okay. So what you can do is just like the example I did in next class, and you can start with df over dx equal to m. Okay. Now m, we know that once we find a b and a c, m we know that is y squared plus 4zx. Okay. And then we integrate both sides with respect to x. Okay, integrate with respect to x. The left side, okay, is df over dx. So you're considering everything else as constant. So this side here essentially just you're gonna get is just f x y z. Okay, you get back to your original function f. This is like antiderivative, right? Okay, and this side here you consider y and z a constant. So you're gonna get 2 zx squared. Okay. Well, generally you're not plussing constant here. So you're integrating x, so y and z are considered as constant. So you're gonna plus the next term, a possible term, which are a function of y and z. Because then if you take a derivative, actually partial derivative, this whole thing with respect to x, this term goes to 0, right? Yeah. So that's your f of x, y, z. So we need to find out what is r of y, z. To find this guy here, we make use of the rest of two conditions. So we do have another condition, df over dy equals to n. Okay. Then what's my n value here, right? N value is given there. So once you find a b and c, you find the n value is this. Okay. Well, I already have my f of x. It's just I don't know what my r is, right? But I can still keep going and calculate the derivative with respect to y. This whole thing. Okay. The derivative, this whole thing, the derivative of this whole thing with respect to y. Then you consider x and z as constant. Okay, so what you're going to get here is going to be just 2xy. Okay, and this term goes to the derivative with respect to y is 0, and this term you get dr over dy. Okay, and the other side is 2xy plus 2yz. Okay, so this 2xy they get cancelled. You will end up with this whole thing here. Okay, then what do? You integrate both sides. Okay, with respect to y. Okay. Okay. Now you consider that as a constant, right? So this side you have here r y z. Okay, will be just z y squared. Okay, but you need extra x term here because you're integrating with respect to y, so there should be a term which is function of z. Okay, so then when you take a partial derivative of this whole side, take antiderivative. Okay, this is called the antiderivative of this term. Okay, then this term will be goes there if we take a partial derivative of to y. Okay, so now I can move this whole thing back over here. Okay, so then fxy, okay, is yx plus 2zx squared plus zy squared plus qz. Okay, yeah. So I do have one more condition with df over dz. Okay, over dz. Now this term here equal to p. Okay, and p is y squared plus 2x squared. Okay, yeah. So then take partial derivative of this whole term with respect to that. Okay, and then you get an equality on both sides. Okay, so the partial derivative of this whole term goes down to 2x squared plus y squared plus q prime of z, right, with respect to z. This is only a z function, so I can just use prime to represent it. Y squared plus 2x squared. So you actually get everything cancelled. So this term equal to 0. This term 0 basically means this term equal to constant c. Okay, so that's how you get everything for fx, y, z. Okay. And in the end, you do an integral. Okay, for the line integral there, okay, you do the line integral. Now, when you do the line integral here, because f is a conservative field, so that's why you don't the line integral does not depend on specifically what kind of curve c is, and it's basically what we call path independence, right? The fundamental theorem of calculus for line integral. That's what we said over in the class. So your line integral, okay, with respect to c, okay, the line along the curve c, okay, is going to be just your potential function at the point B multiplied minus potential function at the A. Okay, yeah. So substitute. You have your point A and B's coordinates. So substitute into your f function, okay, f function, and you'll be able to solve for the line integral. Okay, and you can use your calculator to verify your line integral. Okay. So let's look at problem 5. Okay. So this part here, this is an easy one actually. We see this scalar function show that the curl of del f equals to, so this is like curl of delta of this equal to 0. Now we said when we are taking gradient operation of a scalar function, and we get a vector field which is conservative, and the cross product, the curl of a conservative field is 0, which means the conservative field is irrotational, right? Irrotational basically. This is irrotational, okay? But you need to prove this mathematically, okay? The proof is essentially very straightforward. You know, you just calculate this cross product, okay? As I, J, K. Use the matrix thing, okay? Okay. And del f here is fx, fy, and fz to give you this. Okay, yeah. Now, what makes this 0? What you need to be aware is the partial derivative we learned. You know, fzy. Okay, fzy is a fact. Okay, this is a fact. fzy equal to fyz, or fxy equal to fyx, okay, or fxz equal to fzx. Okay, those are the facts. Okay. So you make use the equality to prove this problem 5. Okay, problem 6 is to use Green's theorem to evaluate the following line integral. So essentially, I don't want you to calculate the line integral using the conventional methods, but instead we use the Green theorem. Green's theorem says we need to convert this line integral into double integral. Okay, and the double integral, the double integral is the R's double integral, right? Is determined by the R here is enclosed by the curve C. Okay, is enclosed by curve C. Okay, so essentially, it's going to be dm over dx dm over dy and dA. Okay, so that's basically, you need to calculate this, and that gives us the line integral, okay, of this. Okay, the a and m, you can find the a and m value over here, right? So this is your basically your n. Okay, this is your m. Okay, like that. Okay, yeah. I'm sorry. This is your m. This is your n. Right. So f function is defined as mi plus nj. Okay. Yeah. So f function is defined as m. F is mi plus nj. Okay. So this is how you can obtain that, right? Yeah, let's continue that. Okay. Let me see if there's any integrals that particularly difficult to you. Nope, I don't think so. I see all of the integrations are fairly straightforward. Okay, as long as you you have your boundaries over there, basically you have all your region R. Just obtain the limits for x and y here properly based on the region R. Okay, then you'll be able to do the integral. Okay, the integral here. So the only thing is, when you have a integral here is 0, that basically means your vector field is conservative, right? Okay. I think that's all the hints I like to give, and let me know if you have any other particular difficulties. Okay. Thank you.